As part of the micro and smart systems course today, we will discuss vibrations, the basics of vibrations as it relates to microsystems. Let us consider microsystems that are shown here. The one on the top left corner is an accelerometer chip. You see a mass where it is suspended by certain beams, which we have analyzed for static deflection in our earlier lectures. Now, let us look at this as a dynamic device, because whenever there is acceleration it is going to move, which we call vibration. Any motion that is periodic in nature can be called a vibration. It does not need to be exactly periodic, but it is a reciprocating motion, something goes back and forth like what a pendulum does. When you have such a system, we want to ask a number of questions about those systems. At what frequency do they vibrate, and what is their frequency response, what is their time constant, and how much time do they take to reach steady state, and if it is a sensor such as the accelerometer, what is the bandwidth of that sensor, what is the response time of that sensor, and many such questions. Below here we have a proof mass suspended by again beams, here 4 sets of L-shaped beams, and this one acts like a gyroscope, which we will discuss in the next lecture. But here again we have a vibrating mass which is connected to these beams, which are characterized by springs. And in the lower left corner, this one, we have this torsion mirror which twists about this beam, which is this red colored beam on either side. This yellow part can twist, the H shaped structure can twist about this axis. That also is like a vibratory motion, because something will be tilting back and forth. And what we show in the top right corner is another kind of mirror. This is a real device that we discussed in one of our earlier lectures, where there is a mirror that can tilt about this axis as well as this axis, a 2 axis mirror. All these are examples of devices that undergo vibrations or small motions about a certain configuration that is going back and forth, oscillations. That is what we are going to discuss today. So, having seen these devices, they look quite complicated, because there are a lot of elements here as well as here, and the twisting of the non-circular shaft, and then here a detail that you cannot see, but this is a serpentine beam. This little one is serpentine beam which makes certain rotational stiffness about this axis to give this mirror 2 axis rotation capability. They all look complex, but when we analyze them, we try to abstract them as simple as possible, and then consider the basics of vibrations, and then we will come back to these devices and then say how we can analyze them. So, let us start with some basics of vibration, and there we have to begin with the concept of harmonic motion. Harmonic motion, that is our starting point for vibration. What do we mean by harmonic motion or simple harmonic motion, SHM as we call it? It does not need to be always simple, but we will start with this basic harmonic motion, where we start with a spring which is attached to a mass, and let us say this can vibrate along this line here. We will measure the displacement of this with x, okay, and let us say that there is a force acting on this mass, let us call that F. Now, when we write the equation of motion for this one, we have to invoke Newton's second law. Let us write equation of motion for this simple spring and mass. Let us say spring constant is k and mass is m. So, if you want to write the equation of motion for this device, we use summation of forces equal to mass times acceleration, that is Newton's second law. So, what are the force acting on this? There is of course the force F that we have applied. These are all the forces Fi, I equal to 1 to n. Here we have F here and also the spring force Kx, that is in the negative direction, because when I pull the mass to the right, the spring will extend and it wants to go back to the original state, and that is why it will apply a force in the negative direction, negative x direction, if I call this as the x direction. So, that force magnitude is Kx, that is minus equal to m times acceleration. Acceleration, as we know, is the second derivative of the position x with respect to time, d square x by dt square, which in short form will denote as x dot, x double dot. X dot is velocity, x double dot is acceleration. Now, the equation, if I rewrite, we will have F is equal to, or let us actually write it as, first on the left hand side we will write m x double dot plus k x equal to F. So, this is the equation of motion for a simple spring mass system. Okay. Now, depending on what this F is, we get different types of vibrations or motion that we describe. The first one, what we call free vibration, is free vibrations, that is when this F is equal to 0, that is there is no force and yet it will vibrate if there is a disturbance. If you leave spring and mass just like that, it is not going to move, but if you displace the mass a little bit and leave no force, after that it will oscillate or vibrate, that is called free vibration. In the absence of the force, external force, whatever vibration we get is called free vibration. And the next one is called forced vibration, where F will be non-zero, F is equal to some non-zero function. Okay. Normally, we keep this as some F naught, some force with a magnitude, times sin omega t, where omega is the frequency of that force. And the third one is general dynamic response. It is not a vibration per se, meaning that if I have a block there and I have the spring, if I apply the force, if the force is large, it will keep on going, and especially when k is equal to 0, the body would start moving. That is the dynamic response of the system, where we take an object, or if I throw a projectile, I take a stone and throw it, the motion of that stone is determined by an equation. Again, that equation will be similar to this, in fact it will be the same, except that you put that force that is over there, and it will not result in oscillations, not vibrations. Okay. So, today we are going to look at these two, the free vibration and forced vibration. Okay. So, let us look at this free vibration. So, we go back to this equation and then say m x double dot plus k x is equal to 0. We are considering the case which we call free vibration, where there is no force. If we look at this equation, it immediately strikes to us that the solutions of sine and cosine are going to satisfy this equation. So, the solutions of this equation have the general form of having sine or cosine, because if I take sine, if I take one derivative, it will become cosine. If I take another derivative, second derivative, it will become minus sine. So, that is what we have here. We have m x double dot plus k x. If x and x double dot have opposite signs, we can satisfy this equation. So, we write a general solution of this equation general solution of this equation is x equal to a sin omega n t b cosine omega n t. So, sin omega n t, cosine omega n t. We could have just put sin t and cos t, but then we know that if it is periodic, there is a omega n or any other constant, it will still satisfy this equation. That is why we call it general solution. In order to see what this omega n is, let us take derivative of this x, that is I write x dot, which is dx by dt will become a omega n cosine omega n t minus b omega n sin omega n t, right, because derivative of sine is simply cosine, whereas derivative of cosine is minus sine, and then we are taking derivative with respect to omega n t, the omega n will also get multiplied. Now, if I take another derivative x double dot, that is d square x by dt square is a. Now, because cosine we are doing, it will become negative omega n square sin omega n t minus b. Now, sine becomes cosine, so it minus n remains omega n square cosine omega n t. So, what we got is minus omega n square times x itself, because that is what we started out, both have minus. If we take minus omega n square out, we get that back. So, what we have now is, if we go back to our original equation, m x double dot plus k x equal to 0. If we substitute what we just got, that is, instead of x double dot, we substitute minus omega n square, and of course, m will be there, x plus k x equal to 0, and x is not 0 in general. So, what we will get is that minus omega n square m is equal to k. That means that omega n is equal to square root of k over m. Okay. And this omega n is called natural frequency of this spring mass model. There is only one natural frequency here, because this mass has only 1 degree of freedom, just moving back and forth. If I take two masses, there will be two frequencies and so forth. What we have considered is a 1 degree of freedom vibrating system, which has natural frequency given by square root of k over m. The units of this are going to be in radians per second. If you want it in hertz, we have to divide by 1 over 2 pi. So, that will become omega n equal to 1 over 2 pi square root of k over m hertz, that is cycles per second. So, many cycles per second. Okay. Now, we have the natural frequency defined. That is a fundamental characteristic of a vibrating system. That is, if there is a system, if you perturb it a little bit, it will vibrate at a certain frequency. That frequency is called natural frequency. This is a free vibration. Now, if you want to determine these constants that we had, if we recall, we had an x equal to a sine, not cosine, we had used a sine omega n t plus b cosine omega n t. Now, we want to determine these constants a and b, for which we need the initial conditions of this system at t equal to 0, wherever you start as a reference time. If we know what x is and what x dot is, then you can determine two constants with these two conditions. Let us say x at t0 is x0 and that at velocity at time t equal to 0 is x dot 0, then we will see immediately that if I say t equal to 0, this will vanish, this will give us that b is equal to x 0, because cosine when t equal to 0 is 1. So, if b is x 0, that will tally, and similarly a will be given by, now we have to take derivative of this, that will become x equal to, so let us just write it, x dot is a omega n sin omega n t plus, actually it is minus because it is a cosine, minus b omega n sin omega n, sorry, this will become, that is correct, but this is the one that will become cosine since we are taking derivative. Sine becomes cosine, this will be there. When t equal to 0, this term will go to 0 and this will remain, that will have a omega n. So, a is going to be x dot 0 divided by omega n. So, we can evaluate the constants, then we get general solution of this free vibrating system. Now, let us look at what happens the case when we have a more complicated system. That is a simple spring mass system. Instead, let us say we have actually a beam. Let us say we have a beam that is hinged at 2 points, but in the center let us say there is a mass. Okay. This has a mass m. This is a typical situation in microsystem devices where we have a proof mass and then we have suspension beams. How do I know the natural frequency of this system? If it were to be just 1 degree of freedom system, meaning that if we were to be able to approximate this as what we had done earlier, that we have this mass which when is restrained by a spring, if I can get this k effective and also the mass m we have, but then there will be an additional mass which we can say something like that added to it, which we will say m effective. That is, this m effective is due to the beam. The beam also has a mass, this is due to the beam, and m is the mass that we have already. Now, both of them will contribute towards the mass of the system, or in general we call it inertia. Inertia is something that an object has because of its mass and that is moving. So, if we can get this m and m effective and kf, we can again write the natural frequency of this in radians per second as square root of k effective divided by m plus m effective. So, we need to find this and this. We have already discussed how to find this k effective. That is, we look at the, for example, if you take the beam theory, this is a beam here, if there is a force in the middle, how much does this beam deflect? Once we know that deflection, we can get the k effective. That is, let us write it here. If I were to have this beam, that this we have already discussed, we are doing it again. If there is a hinged beam with a force F acting here, whatever that force is, when it deflects like this deflection, if I call that delta is given by this F times L cube divided by 48 EI, where L is the length of the beam, L is the length of the beam, and E is actually we have been using y, so that there is no confusion with the electrical field that we will encounter later in this course. So, we are using y for Young's modulus and I is the area moment of inertia. Okay, that is the thing. Now, if I want to know K effective is simply F by delta. If I do that, I get this as 48 yi divided by L cube. Now, how do you do M effective? Before that, let us actually see what is the basis for getting the K effective this way. And the basis really is, if I look at the strain energy, a concept that we had described in one of our earlier lectures in the context of applying Castigliano's theorems and other energy theorems. If I have this strain energy, which is defined as integral of stress times strain, half of that integrated over the entire volume of the elastic body, in this case the beam. If I do this and equate the strain energy to half this K effective times motion of just this point. Now, let us call this motion of this mass as y. Okay. Then I simply say y square, as if the spring is moving and spring extension is y. Okay. That is how we obtain this K effective that we have shown here. In other words, half K effective y square is equal to the strain energy stored in the continuous beam. Similarly, when we want to get the effective mass, we would try to get effective mass such that half M effective times y dot square, that is a kinetic energy. If I have a mass that is moving with a velocity v, its kinetic energy is half m v square. Here that velocity is time derivative of this y. Okay. So, if I know that y, half m effective y dot square should be equal to kinetic energy of the whole system. So, whatever we have done now for the strain energy, let us do this for the kinetic energy also. So, the kinetic energy, which we denote by K E, kinetic energy is equal to, if I take a small particle with volume dV and density rho, that is its total mass, that mass multiplied by y dot square, okay, where this y could be the extension. So, let us write it generally. Okay, if I take the go back to the beam, we have this beam which is hinged here and here. Now, when it starts vibrating that way, this way, whichever way it wants to vibrate, when you have that, let us denote this as W x, where x goes from here, x equal to 0 here, x equal to L here, then W x is displacement, and dW by dt, W is a function of x and t. So, W is a function of x and t, because every point is moving with respect to time and also it varies along x. So, we can take derivative with respect to x as well as t. dW by dt is, or we can call it Wt, is the velocity. So, if I take want to write kinetic energy for this, I will write W dot square and half will be there. We have to integrate over the volume. We already have dV, integrate the volume. In other words, what we have is half rho W dot square dV. Okay. Note that this is not omega, this is actually W. So, this one is W dot. Okay. That is the velocity of each point in this beam. Now, this kinetic energy that we have here, okay, this kinetic energy, we want to equate it to half m effective times y dot square. Y dot, if you recall, is simply the motion of this mass and of course, the beam at that midpoint. Okay. So, that is what we would like to have. So, how do we get this W of x here? If I take that and then integrate this, whatever I get, if I can put it in this form where m effective can be obtained. So, now this W of x that we are talking about here can be written. I am not writing the time dependence, just writing the x dependence, because we can write this W of x as something that depends only on x and then something that depends only on time. What depends on time usually will be, in the case of vibrations, a simple harmonic motion or harmonic motion sin omega t. Omega can be anything, omega n it can be, omega or any other frequency. So, we only look at the x dependence, because that is what we need here in order to integrate. So, W of x here will have this form, which is W max, which in this case happens to be at the midpoint, that is your W max times 3x by L minus 4x by L whole cube for x by L less than or equal to half. Okay. So, we can put this W of x into this integrand. So, this one goes into this integral, then we get that K E here, which turns out to be, when you do the integration, by the way, this W max is nothing but what we call y that we have here. Okay. So, here we need to put W dot. When we take this W x, when we take the derivative of this, these depend only on x, where W max keeps changing. So, W dot of x, which we need, will be W max dot, that is dW max by dt times the same thing. Whatever we have here, the same thing will come down. So, W dot here is W max dot times something depends on x, we substitute over there, and notice that W max dot is nothing but what we call y dot here, because if we go back again, we say that that is the motion of that midpoint. So, now what we get, this integration, when we do, we get it as half 0.4857 m into y dot square. Where does this m come from? This m comes from this rho, that is a mass per unit volume. This quantity rho is the mass of this per unit length, because we do the area also is taken. If I say this rho is m by L into A, this A and this A will get cancelled, that is A that comes over here and that A that is there in dV, both if I cancel, I will just have m by L. So, that m is coming because of that. Now, if we take this K E and see that it is actually should be equal to this, then what we see is this quantity here becomes our m effective. So, m effective is 0.4857 times the mass of the beam. So, if we go back to our primary question, if I have a beam with some mass attached to it, that mass is capital M that we have, like a proof mass in an accelerometer or gyroscope or any other MEM structure. If it is pinned here and pinned here, then this becomes equal to a spring with K effective and two things here, M plus M effective, this is K effective, which we have already gotten it as 48 EI by L cube, and this now we get M plus 0.4857 M, where M is the mass of the beam. So, not all of the mass is moving as much as this y dot, that is motion of this, we said y, okay, y dot is dy by dt. This mass here is not moving at all, this mass is moving little bit and this is moving a lot at the center. That is why only less than half of that mass of the beam becomes effective mass. So, this is a simple technique that we can reduce any vibrating system, however complicated it is. If you want to reduce it to 1 degree of freedom, that is just 1 x, then you have to find the equivalent mass. This we can do for all the complicated things that we see here. So, if I take let us say this gyroscope, in fact it will have 2 degrees of freedom, meaning that it can move in the x direction or y direction. So, we have to go back. So, let me get a pen here. Okay. If it vibrates in this direction, this proof mass vibrates in this direction, or it vibrates in this direction, then we can reduce it to something like this. We can reduce that to, here is a mass M with a spring here and a spring there and a spring here and a spring there. Okay. Now, this can move in both x direction like this or like this. Okay. Similarly, if we take this, that can reduce single degree of freedom, this can reduce 2 degree of freedom, because this can oscillate about that axis as well as this axis. Either way, there is a resistance for it. It is a spring, torsional spring, which we discussed in the last lecture, and that can be taken into account again using this method. The idea is we have to find M effective such that half times M effective times the velocity square of the point that we are considering, in this case could be center of the proof mass, that should be equal to total kinetic energy of this system, and K effective we take strain energy and get the equivalent lumped constants. Okay. So, now let us go back to our discussion where we want to find the natural frequency of this. So, now natural frequency omega n is simply going to be equal to K over M, meaning effective K effective divided by M plus M effective, because we have the additional mass at the center, that M goes in there, and that is how we get the natural frequency of this system. Likewise, we can do this for any other system that we have noticed here. Okay. Now, let us move to a second level, where in dynamic systems we have inertia, the mass, and we also have the stiffness K. That is what we have considered, spring mass system. Now, we move to another level where we say mass, spring, the two things that we have already discussed, damper system. All of us are familiar with the concept of damping, which is something that tries to oppose the motion or retards the motion, that is a better word, retards the motion. If there is friction, if I am moving, it will resist my movement. Similarly, if I have a pendulum hanging, when I set into oscillation, if you come back after 1 hour and see, oscillation that you have set up has disappeared. It has disappeared because it has damped out those oscillation. What has damped out? In the case of pendulum, it is the viscous damping, that is the air damping around. Similarly, if I put a ball in water, if I push it, it will keep on going up and down like this, after a while it would have stabilized. Again here the water viscous damping that is acting on the ball would have reduced it. So, now let us consider those systems where we have a spring restraining our mass, but also we have another restraint which is the damper. So, spring constant K, the damping coefficient we put it as C. So, C is damping coefficient. K is stiffness, M is inertia or mass, C is the damping coefficient. Now, what happens? If I take free vibration of this, that is I have taken this mass, moved it by certain amount and left it, then what happens? So, for that the equation of motion now will involve the effect of damping, and this damping, the force due to the damping is C x dot, force due to damping. So, if I again take this as x here, it is moving, C times dx by dt is the damping. If that is a force, we can write the equation here, whatever we had earlier, m x double dot plus C x dot, that is a force due to damping, plus k x equal to 0. Okay. When you want to move this here, we know that inertia force, when I move in this direction, the force that will act in the other direction will be m times x double dot, that is acceleration, m a is equal to f, right, that m x double dot, and the damping will also pull it this way, k x also pull it this way. These are the three terms that try to balance out the force that is applied on the mass. That is true in general. Inertia force, damping force, spring force, all of these are going to try to pull you back from the direction in which you are applying the force. Now, how do you solve this equation? When this term was not there, we just saw that sine and cosine were the solutions, but if they are there, now we need to find the solution. For this, the easiest way is to take the Laplace transform of this equation. Let us write the equation again, m x double dot plus C x dot plus k x equal to 0. If I take Laplace transform, I hope you are familiar with the concept of Laplace transform. If I take Laplace transform, then I will get this as m s square plus c s plus k equal to 0, or I will try to make this just s square by dividing by m equal to 0. This is a quadratic equation. Then there are two roots for it, S12, which will be minus c by 2m square root c by 2m square minus k over m. Now, general solution of this is going to be a times e raised to s1t plus b times e raised to s2t, that is the general solution of this differential equation. If we substitute this back into this equation by taking x dot here and x double dot, you will see that it will match up and give you the solution, where S1, S2 are given by solution of this characteristic equation that we get when we take Laplace transform and of this equation. This is the characteristic equation. Okay. Now, if this is a general solution, there are certain things that we can say based on different conditions of damping. The first one is when c by 2m square is greater than k over m, we call it overdamped oscillator. There is a lot of damping, overdamped. Second one is when C by 2m square is equal to km, we call it critically damped state. Okay. In fact, in that case we can define a Cc which is Cc square by 4m square. I am just squaring here, that is equal to km. So, Cc is going to be equal to 2 times square root of mk, because one m another m, this cancels and there will be mk, and then 4 into a square root, it will be this. The third case is where you can guess what the third case is, simply that C by 2m square is less than km, which we say C is less, that will be underdamped. Okay. We have 3 cases: overdamped, critically damped, underdamped, and for that we can define something called damping ratio, which we denote with this zeta. So, here that zeta equal to 1, here it will be less than 1, here it will be greater than 1. Okay. This damping ratio is a indicator of how much damping is there. If there is lot of damping, we call it overdamped. If there is just sufficient damping, sufficient for what, that we will see something called a critically damped state. Other one, if we have less damping, we call it underdamped state. What does it mean? Let us look at this here. What we see here is that the first case, when this zeta is equal to 0, we have this curve. This is no damping. So, this means that if I start out, we are showing here time, just multiply omega naught, does not matter, just the time, and here we have the ratio of x t at any time t divided by what it was at the beginning, just normalized. So, if we start here, it will just keep on oscillating, that is, if I have a pendulum, it will keep on moving with the same amplitude that you set out with at the beginning. If there is no damping, it will just go on. Now, if you take this case, that is a blue curve, it will go like this and then oscillate, after a while it die out. That is what happened to real pendulum. It you set into a large motion, after a while it will reduce and reduce, and finally it will just come to a rest. Now, if you look at the case of critically damped, it just comes down like this. If it is overdamped, that is greater than 1, it comes down this way. Okay. So, each of these has a different behavior. So, the critical damped is the transition behavior, where the oscillations you do not see. This is overdamped, where your zeta is greater than 1, that just goes without any oscillation, whereas when it is less than 1, that you see here for this blue curve and this magenta curve, there will be oscillations. Okay. When it is 0, which is this curve, it will not reduce at all, oscillation amplitude remains the same. Between overdamped, no oscillations to oscillation case, that is our critical damping, where that Cc or we said zeta equal to 1, and that is what it means. If there is damping, it will quickly stabilize. If there is no damping, it will keep on oscillating by the same amplitude that we set it out with. So, now let us go back here and then try to see the significance of this damping in the dynamic systems that we encounter in microsystems. Okay. Now, particularly if we have this zeta greater than 1, okay, if you say that zeta, actually greater than 1 is not so interesting because there are no oscillations. Let us take the case where there is less than 1, that is the underdamped case, underdamped case. Now, as we saw in that figure, if I start out, this is x, this is time. If I start that x with some disturbance, that I pulled it and left it, then it will go and then it will go back. Now, if we look at this envelope here, where the amplitude of this oscillating is decreasing, okay, and that curve will have some constant times e raised to minus zeta omega n t. We already talked about what omega n is, natural frequency. Now, it will be exponentially, it is decreasing, the amplitude from here to here to here to here, it is decreasing, that is what we see. So, now if I were to look at the solution, we have that S1 and S2 that we have derived here, S1 and S2. If we substitute them back into this general solution that we have written, which is over here, we get something like this. We get this x to be e raised to minus zeta omega n t times a sine square root of 1 minus zeta square times omega n t plus b cosine square root of 1 minus zeta square omega n t. Now, previously we had only omega n, but now we have omega n times the square root of 1 minus zeta square. This thing is called damped natural frequency. We had defined the concept natural frequency when there was no damper. Now, we have a damper, we call it damped natural frequency, which is square root of 1 minus damping coefficient square times omega n. Okay. When this is 0, there is no damping, it reduces to omega n. So, this is a general one. Now, if we want to know what this damping coefficient is for a real system, let us say a built-in accelerometer, and you want to know what the damping is, we will discuss that in one of the future lectures, but now we will just see that you do not know how to model it, but you want to know what it is. You can determine that from an experiment. If you take a microsystem device, you set the proof mass into some motion, and if you can capture that motion, you can measure the motion of something in various ways. The most direct way is to have a vibrometer, a laser vibrometer for example, will give you the motion as a function of time. If that function of time looks something like this, then if you can measure at what rate the amplitude is decaying, that is if you can measure this quantity, then we can estimate what the damping coefficient is, because we would know what omega n is, natural frequency, that is k effective, m effective. If you do square root of that ratio, if you take that, you will get omega n. Now, we want to know what the damping is. For that, what we need to know is, or omega n experimentally, you can just see what this time period is. So, if you take one oscillation, let us say it is 0 here, again it is 0 here, this one if you can measure, that is your time period tau. Tau is the time period here, inverse of that will give us omega n. Okay. And now, if you want to see this will be time period under damping. So, we will say tau d, because there is damping here, otherwise it would have been just normal time period. Now, it is tau d, and we can take that tau d and try to determine what will be the omega d here and what will be this zeta. So, for that there is a technique where we call it delta, which is logarithmic decrement, because something that is going exponential has a logarithmic nature. Logarithmic decrement is simply the natural logarithm of x1 and x2, that is x at 2 instants. So, I take x there and x here, I take the ratio of these two, take the logarithm, that can be shown to be equal to, again if you have x here evaluated at some point and then you evaluate not immediately afterwards actually. If you take it here, you have to take a similar one over there. So, if we take this is x1, you take here x2, okay. That is after one period if you take, then that can be shown to be equal to zeta times omega n times tau d, okay. Now, we know this because we can measure it, and this logarithmic decrement we can measure it, right. All of these things we know, then we can compute this zeta or damping coefficient. This is a very useful thing, because if you have a vibrating system, if you can measure its free response when it is damped, if you can get the time period which you can measure once you have a waveform like this, and you can compute its natural frequency, and if you can compute this logarithmic decrement, that is x1 amplitude at certain point and one cycle later, if you can get x2, the difference of the ratio of this logarithm, that if you equate it to these two, this unknown thing becomes your damping coefficient that you can compute. It is very useful in experiments. Now, let us discuss the forced vibration. So, we have forced vibration where we had the equation m x double dot plus c x dot plus k x equal to f naught, we will say equal to sin omega t, that is a periodic force. If we have that, the general solution will be same as what we had earlier. Okay. Now, we can also write a particular solution for this force that we have, x then will have whatever solution that we had earlier. In addition to that, we will get a particular solution which will be of this form, where x is just some constant times sin omega t, the same frequency, minus some phase phi. So, this phi is called the phase difference. That is, if there is a system that naturally vibrates at one frequency, if you have a force that is being applied at another frequency, resulting solution will have that frequency, natural frequency, as well as a new one. That is why there is a phase lag between the two, that is the phase. The solution of this can be written in this fashion. If I give you x and phi, we are done, because omega is already given. So, x here, the amplitude is given by f naught divided by square root of k minus m omega square plus c omega square, and this phi, which is the phase, can be written as arctangent or tan inverse c omega by k minus m omega square. Okay. Now, this part can be rewritten in a convenient way, f naught divided by k square root of 1 minus m omega square over k square plus c omega by k square. We have basically divided by k both the numerator and denominator. The reason we do this is to see a pattern in this, f naught over k divided by square root of k over m was omega n square. So, we get 1 minus omega by omega n square plus this portion turns out to be 2 into zeta omega by omega n square. So, this gives us a way of visualizing this amplitude x as omega varies. This is the amplitude and phi amplitude, and this is the phase. We are interested in the amplitude. If we plot that using this expression here, we get something like this. Let us say I plot here omega by omega n, and here I have k x divided by f naught, okay, because that is what we are interested in. If I plot this k x by f naught, if I take this, that is if I go back, this f naught will go denominator, k will go to numerator, that is k x divided by f naught 1 over this quantity, that is the denominator of this quantity. If we plot that, it is going to look like this for various values of damping coefficient. When damping coefficient is critically damped one, if I start here, let us say that is equal to some value that we have started out with, it will go like this. Now, if I take it to be slightly larger, let us say this is the is equal to 1, that is a critically damped case. Critical damping, it is going to look like that, and if it is more than critical damping, then it would go like this. If it is less than critical damping, then we will see a behavior like this. If it is further less, it will be like this, and if it is 0, it will go like this. Okay, this is the case where zeta equal to 0, no damping. All of these peaks occur at omega equal to omega n, or in this plot it will just be 1. Okay. That is at the natural frequency. When the applied frequency is equal to natural frequency, we see something like this, that is it will go to resonance. That is a condition of resonance, which we try to avoid, or in some microsystem devices we also take advantage of it. Now, if I were to zoom in this portion, okay, then we would see, let us look at this in a plot. Okay. Okay. Now, we are looking at the frequency and amplitude on this axis. What we see here is that at this natural frequency, that is here is where omega is equal to omega n, we have a peak, and this is linear, and also notice that this is on a log plot. Okay, this is log plot 0.01, 0.1, 1, 10 and 100. Over a region it is constant. That means that the amplitude here is independent of the frequency, and that is what we call it as bandwidth. Okay. So, whenever you have an oscillator, spring mass oscillator, that is the bandwidth. So, we will discuss this bandwidth and how it relates to sensors in the next lecture. Thank you.